Good evening, everybody. Welcome to League of Extraordinary Inventors. I'm your host, Mike from Faraday Research. It is Friday night. It's April 5th, 2024. Welcome to our live podcast. We're doing it live on, excuse me, we're doing it live on YouTube right now, and we have the live chat open. So if you're joining us now, want to ask questions, make comments, whatever, live chat is open. So backstage is open. I sent out my invites if anybody wants to join the conversation. Make sure you have a headset, webcam, and just follow the link for the show. I'll put that in there here in a second. And we're supposed to have Gerald in tonight, so hopefully he's going to join us soon. Probably Mike is probably going to join us from Florida. So it's been a busy week for everybody. Had Easter, happy Easter, belated Easter, and to start the week, my whole family got sick. We got the Norwalk virus, and we went to a party, and almost everybody at the party within a day or so afterwards got sick. So we were really sick, like bad. So that kind of killed the first part of my week. But the last part of my week has been very productive. I've been working on the new battery cell. I'll be talking about that later on. And I've also done some experiments with the Renegade, which were pretty encouraging. And it's overall the whole week has been busy. So that's a good thing. Philip, thanks for joining us again tonight. Maybe we'll just start off with you and see, give us an update on what's going on.
Yeah, thanks, Mike. So I'll do like what I did on APEC last week. I'll do a retrospective on all the experiments I've been through.
Okay.
It's going to be quick. So some of them you already saw them before, but the last two ones is what I did 2 weeks ago.
Right.
The MHD vortex experiment. So I'll show you the results of that.
Okay, that sounds good.
And yeah, so I'm gonna
How was
start.
your Easter, by the way?
Sorry.
How was your Easter, by the way?
I just stayed here. I didn't see family. I didn't. I just stayed here in Montreal. So and watched some hockey. So nothing special for me.
Yeah, exactly. Yeah, we did too much of the family thing, and I think it backfired on us.
Yeah.
So well, that's the way it goes. But we make good use of our time, and been doing a lot of experiments. So yeah. All right, so let's put this up on the stage here, and you can kind of go through it with us.
So can you see my screen?
Yep.
So that was the grinder experiment I did before going to the tech conference in Washington, D.C. at the end of November.
Right.
That was the experiment I showed to the PhD of Lockheed Martin and all that. So I'll play it again.
That's definitely showing a deflection.
Yeah, so we see a weight loss when the wheel is spinning. There's a weight loss right there, and then when it starts spinning, it gains back its weight.
Right.
And that was the first experiment that I did. I did another one in August.
I never asked you this question before. You know the old experiment with the gyroscope, where you spin it and you could actually balance it on a string.
Yeah, we tried the gyroscope, but the gyroscope wouldn't stay still. It would move all over the place, so it was hard to. Yeah,
I've done that experiment years ago when I was a kid. I had a gyroscope, and I did that experiment, spun it, and actually balanced it on the string. So, and that what it was showing that it was exhibiting a force longitudinally outwards and fixating it in a position where gravity didn't have an effect on it anymore. Because if it did, it would just fall off the string,
Yeah.
right?
Yeah.
So that means there is a force there. So if you got a force going this way on the flat plane, and now all you need is the force to fixate you in space this way, then that string, you technically should be able to remove it and it should stay exactly in one spot in midair. So that's showing me that it does have an effect on gravitational effect from the sky to the ground
Yeah,
because
exactly.
because you're
So that's what I forgot to say. That's the when you have a spinning wheel, it creates a gravitomagnetic energy density, and the energy density is responsible for the acceleration, the gravitational acceleration, which changes the weight. When you change the weight, then the balance is going to measure something different.
right,
So it's like it's the same thing as electromagnetic energy density, gravito-electromagnetic energy density are the same thing. You create some, it's gonna create an acceleration, time
right,
dilation, and temperature change. Well, I can't test the temperature change, but I know it's gonna change as well.
right. So uh, how much like does it go up in temperature or falls in temperature?
Yeah, so the denser the energy density will be, the colder it's gonna get.
Right. So superconductivity, yeah.
Yeah. Yeah,
Which
that's a good relation right there,
yeah,
and
because
that's
the way I see it, because if the force of gravity is going down like this, and you got a spinning mass going in this direction, instead of the forces of gravity pushing down, now they're getting deflected longitudinally outwards
yeah,
because there's really no other logical explanation why that gyroscope would actually stay, uh, you know, there
yeah, I know, I
in
know, yeah,
space.
yeah. It's like
So
when
it
you, yeah, when you ride a bicycle, the faster you go, the
right.
more
So
stable you are.
so you're canceling out the gravitational effect going down, so it's keeping the gyroscope up. So that means you're forcing the force of gravity this way. Okay. So now you have to develop a disk that will spin this way and cancel the gravitational effects of it going down. Then technically you should be able to remove the string and it would fixate itself in space. Now I think there's a little bit more to it than that. You probably have to go at super high velocity speeds and get the superconductivity that we've been talking about, and temperature loss in that space would technically give you gravitational, um, you know, uh, dilation. So
Yeah, yeah, interesting. Um, yeah, I need to
now,
do.
now, say here, I don't know if you've done this yet. Um, have you tried charging the disk at a high voltage while spinning it, like electrostatic?
No, obviously no, not yet, but I can easily do that now that I have a car battery charger
Right.
that sends like 120 amps.
No, I understand the amps. I'm talking electrostatic.
Oh, okay. Yeah, so, but it's gonna create a magnetic field. If you spin an electrostatic disk, it's gonna create a magnetic field.
Right. So,
Um,
so I'm thinking if you spin that disc at say 20,000 RPM, and then
yeah,
get yourself a Van de Graaff generator connect a wire from the bulb of the Van de Graaff generator to the shaft of the spinning mass.
Yeah, and can kind of measure its mass somehow.
See if it increases the effects.
Yeah, exactly. Um,
So, like, because I know some Van de Graaff generators can generate up to 100,000 volts. Maybe that's what you need. Charge that disc up to 100,000 volts. Now, here's another experiment you can maybe try. Make that spinning disc into a capacitor, like Townsend Brown used aluminum foil, paraffin wax. He was using tar and actually making those discs that he was charging into capacitors, and then
okay.
hit it with the Van de Graaff generator power, get it charged up to 100,000 volts, and then spin the hell out of it and see what happens. I think that would be pretty impressive to see what would happen.
Interesting. Yeah, yeah, that would be. Yeah, I need better labs right now. Right now, I'm doing that stuff at home, but
Yeah, but you can make these discs into capacitors at home. It's not expensive material. All it needs wax, maybe some tar, and then aluminum foil, and you make that into a disc, into a very tight disc. But it's going to have capacitive value now. If you can get that disc have capacitive value, but then you hit it with 100,000 volts, you might have something there. I think it
yeah,
would. I think it will make an effect.
yeah,
Mikey,
yeah. Thanks. I'll check it out.
yeah,
I'll talk to you later about that.
yeah, because
Um,
that's stuff what Townsend Brown was doing back in the 1920s.
okay,
So yeah, Mike's in the live chat. Mike, if you want to join us, hop on. Um, I'm going to put the link for the show here in the live chat. Let's do that right now. Put the link there. Okay, it should get posted now. Mike can join us. Hopefully, Gerald will join us because he missed a couple of weeks there. But that's okay. That's the way it goes. Yeah. So yeah, carry on with your presentation here. Sorry.
okay. So that's the Harvard trip balance that the PhD of Lockheed Martin asked me to do. I'm still using the grinder, but
Right.
I think I showed that before, so you know the results.
Yeah. Yeah. We've seen that.
Yeah, so we can see that it stays down. So it's not
Yeah.
just an outburst of wind or a burst of energy or anything like that because it just stays down.
Right.
So it kind of gain weights this time. Um,
And it's directional. You can change the direction of it if you want.
the yeah the I mean I did try upside down the other way like 180 degrees.
Right.
I flipped it 180 degrees and I still got a weight gain. So I was expecting a weight loss, but I still got a weight gain. So
How about the direction if you go from clockwise to counterclockwise?
yeah, well, if you flip, well, yeah, if you flip it upside down, you're gonna change the clockwise,
Right.
counterclockwise
Yeah,
direction.
you're right. Yeah.
Um, but
Uh,
if it's sideways, then it's gonna lose weight like you just saw.
loses weight, eh? Huh.
Yeah, like you just saw. So I gotta redo the maths of that because I was expecting a weight loss. If you flip it the other way, I was expecting the other way
How about
around.
how about the thickness of the disc that you're spinning, does that have an effect?
Yeah, I'm not sure. There's not like plenty of discs we can use for the grinder, so maybe I can buy a thicker or thinner disc and try
Yeah,
it out
just
again.
what's the disc made out of that you're using now? Graphite?
I think so. Yeah.
Yeah, you could probably get, go to a machine shop or whatever. Just say you need a graphite or even a steel or aluminum disc. Tell them how wide you need it, what the diameter is, put a hole in the middle, and then fix that on there and see. I guess you would have to experiment with different materials too. What works, what doesn't work.
Yeah. Yeah. Yeah, I can try that later down the road. But just just the direction it's strange because the direction didn't change anything. But if I flip it like sideways, then I'm losing weight. So or I don't know. I need to redo the maths or something like that. But yeah, just so that you do a heads up on the results.
Yeah,
And this is the interferometer experiment I did also. That's a interferometer, like a laser with mirrors and
yeah,
lenses and all that. And I'm moving a magnet up and down next to the laser, and the final laser is projected on the wall. And here's what we see when I move the magnet.
it's like a distortion. Or,
Yeah, so we see the laser is being moved by the magnetic field. So it is
right,
affected by the energy density of the magnet. So yeah, that was my theory that the energy density of any form, electromagnetic or gravito-electromagnetic, would change the acceleration, the time dilation, or and the temperature,
right.
and it seems to be confirmed. And
That's
this
cool.
is I already showed this before. This is the Cavendish experiment.
Right.
So what I
That
found is that there was indeed a deflection, an attraction towards the bulbs. I also
Yeah,
tried
yeah, yeah.
putting the arrays of bulbs
That's a pretty cool effect.
inside of the box with the balance. Finally,
so we saw that the rod is being attracted by light by the energy density, even when the right after the light is being turned off, because of the light is still being infrared light at that point,
Right.
which is still electromagnetic energy density. So
Yeah, I'll get to the point where we can't visibly see it, but the ultraviolet's still present and it's still being attracted.
yeah,
Yeah, that's
the infrared, you mean?
yeah.
Yeah.
Excuse me 1 second. I just have to go blow my nose. My nose is going crazy here. Hold on.
So, Philippe,
Hey, Mike, how's it going?
bon,
Is,
c'est bon.
is it
Boy,
is it warm in Florida right now?
It's nice and cool.
Nice.
Not
it's
not
colder
Do
not
here.
you do
not
you live
freezing right
next
now.
to the beach?
Yeah.
Must be nice.
Yeah.
How much snow did you get in
Uh,
Montreal?
sorry.
How much snow did you get in Montreal?
Um, right now, uh,
Oh,
right now it's 3 Celsius.
3 Celsius. Yeah, we didn't get any snow. There was a storm that went through north of us, got like 25 centimeters. We got nothing. then
Oh yeah,
then I heard Ottawa got hit.
yeah, yeah.
So
We had some snow this week, but it melted down very quickly. Um, so yeah, to resume my presentation, here's the long-awaited MHD vortex experiment that I did at home, instead of waiting for university or professional labs. I just did it at home with the help of my great lab technician assistant, and he helped me a lot for that. So thanks to Chris for his help. And so, anyways, here's the results of the MHD vortex experiment. So we can see a weight gain. So I'm sending 120 amps. I'm sending 120 amps, and we can see it gains weight again. So there is a acceleration shift again. Um, and now I flip the direction of the current. So I just flip the electrodes, and we'll see what happens. Yeah. So I still got a weight gain. So I'm getting the same thing if I change the direction of the vortex here again. I'm seeing the weight gain again. And so yeah, I was expecting a weight loss, but I'm getting a weight gain in both direction. So it's the same thing like the grinder. I'm getting a weight gain, but if I put it sideways, then I'm getting a weight loss.
right. So it
Um,
seems so it seems like if say gravity, just my theory, if gravity is actually charged, there's a charge in gravity because the disk is upright like this horizontally and you're spinning it at high speed, it doesn't allow the gravitational forces to adhere to the surface. And because you're spinning it, any charge of gravity that's influencing that disk is now being spun away. Therefore, that's why you're getting that weight loss. Now, if you're this way, now the gravity and any of the charge of the gravity particles are hitting the surface, that creates weight gain. So by showing your experiment, by adding several amps to a surface or a body, when you add charge to it, it increases mass. So
yeah,
now,
it's a vortex of gallium that is spinning inside it.
right.
So, but you thinking of gravity like graviton? Is that it? Do you see gravity like
Well, it's obviously it's a it would have to be a form of a particle if it is hitting a surface and exerting a force, right, on that
yeah?
surface.
But what's with the mass? Why is it mass seems to affect gravity?
Well, because you're charging it. If you charge it, the
No,
gravity,
when it spins, all you gotta do is spin it.
right? If you spin it and there's no charge on it, it loses mass. If you spin it
Even if you spin
horizontally,
it, it still affects gravity, just as mass by itself. No charge, just the mass
right,
spinning
right.
will
That's
affect gravity.
Yeah.
If you sit in a chair and spin, pull your legs in. Why do you spin faster? You're not touching the ground. You're not pedaling the ground faster, are you? No. But somehow your repositioning of your mass is spinning you faster. That's centrifugal force,
right.
centrifugal.
Right.
Somehow the mass spinning is creating this charge that we're talking about.
Yeah,
This
it's reacting.
polarization of the mass.
Well, it's reacting to the say gravitational force, and it seems like gravity has some kind of
So maybe the
electromagnetic
spinning mass is grabbing
electromagnetic.
some of the gravitational force and spinning it with it.
Yeah, that's on my end. My theory is that it creates
Well,
the
because hold on, doesn't
electromagnetic
gravity
field.
affects mass, right? Gravity has its force on mass. If there's no mass, gravity has no purpose. What's it going to affect? There's nothing out there else to affect that we know that gravity can get its
Well,
hands on, other
don't
than
forget.
mass. But when the mass is spinning, the mass is, we already know mass has a connection to gravity. So when you spin it, somehow it's connecting to gravity and spinning it.
Right, but
The gravity, spinning the gravity,
don't
because it's
forget.
mass and gravity connects to mass. And if you spin the mass, gravity is spinning with the mass
Don't forget
because
too.
it's connected to mass. What else does it affect? Nothing.
Yeah,
Nothing
don't
that we
forget.
know in the universe does gravity can affect
Don't forget
other
too.
than mass.
We're on a planet and we're
I
traveling
mean,
around the
not
sun.
matter also, but mass
We're,
is matter also.
yeah, we're traveling through space as well. Don't forget, we're on a planet that's moving how many thousand kilometers a second through space. So if gravity emanates from the cosmos and becomes more apparent to us when we're on a large body like the Earth, okay, would explain why on a smaller body such as the moon, we lose about 60 to 70% of our mass when we're on the moon. Makes total sense because the moon is moving through space.
The
We're
moon is
moving
also smaller than the Earth,
right,
less
but what I'm
mass,
saying it right,
less effect on
but
gravity.
that's right. So the bigger the planet, the more you weigh. So for
Well, I
say
mean,
you
there's smaller planets that have more mass. It all depends on their density.
well, yeah, the density of the
Keeping
planet,
that in mind, as long as we understand that, we
like they
can
say it,
understand.
yeah, they said, if you go on, say like Jupiter or Saturn, your weight increases by like 20 times just because of the
Right.
sheer size of that celestial body, right?
It's more dense and it has more attraction to at least this gravity force. It has more attraction to it.
You see, a lot of
Uh,
people don't realize, we're like right now, okay, say like this cup of
like the,
coffee.
the 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 singularity of black hole is so dense, or whatever, the center of a star is so dense that it collapses on itself
Yeah.
because of that density. And what helps it collapse on itself is the outward force of gravity on it.
See,
Or
like Eric
if
Dollard, he
gravity
had a
is even
really
an outward force, nobody even knows.
Eric Dollard had a really good
Outward.
analogy of it. If this cup of coffee has a lot of energy, okay, we're traveling through space at like 500 kilometers a second around the sun. We're going really, really fast. So, say I were to throw this cup of coffee off the train, it's going to make a huge boom. There's a lot of energy sitting in this cup right now that we don't realize because we're sitting relative to its space. Okay. So, that would explain a lot of stuff with what's happening with gravity too. If there's a relationship there because we are moving through space. If gravity comes from the cosmos, that's where it emanates
I
from.
mean, maybe by giving the mass charge, you're giving it more. I'm sorry, by giving the matter, aka the gallium, charge, you're giving it more mass
Right,
because energy is mass.
right, exactly. So say you reverse that effect, okay? You super cool that gallium. Now it's going to get lighter. And they've already proven that theory
Because it
with
loses
magnets.
mass when it gets colder.
Yeah, like you take
Oh, that's interesting.
right? Because when you take magnets, right, and you drop them in, say, into uh, dry ice, right, and you bring them out and you spin it over, it will hover above the ground over a mag. It'll hover in its spot. It'll go into a magnetic lock. So that's pretty well proven. So I would say start supercooling the gallium. You're going to get weight loss.
That's
Going the
interesting.
opposite.
And I never thought of
And we
that.
still skip the basic fundamental question. Why do you why do you speed up when you pull your legs in on a spinning chair? Nobody has an answer for that.
Well, you're increasing the surface area of the mass when you're wider like this. So when you
Oh, actually,
go,
when you pull your legs in, you're decreasing.
you're decreasing, which it increases your speed. When you go outward, you would slow down because your mass is now larger. Your volume spins
And you know
around you.
that's a you know what, if that's true what you just described there, which makes sense. If that's true, that also leads an indication for a completely magnetic influence on the geometry of things. So changing your geometry changed your magnetic influence on the environment. By pulling your legs in, you changed the geometry. You also changed the magnetic influence of the rest of the pressure around you. The pressure is the environment.
Guys, I don't
There's
think they
pressure
like
in
what
you.
I think they don't like what we're talking about. They're killing my internet here.
Yeah, the CIA is
Yeah,
blocking
You on a
it.
Wi-Fi again?
Well, I got a good connection. I'm like 500 megabit
Your
down.
router's probably burning out.
No, probably I'm getting hijacked by somebody. They don't
Routers
like
don't last that long. 5 years maybe.
this one's only 2 years old.
Sometimes they don't last more than a year. It depends on the manufacturer.
Are you with
Mhm.
Rogers?
No, I'm with a
Wireless
third-party
router.
company. It runs
Yeah.
it runs off the Bell lines. It's a high speed.
Okay.
But I never have problems with it until I do this show and then I get hijacked. Like,
Laminar flow effect. I don't understand that. Yeah. Water
Yeah.
around the rock is in a river.
So yeah.
So yeah, I would super cool your gallium for sure.
So do
Okay.
you want to show your over Unity battery?
Yeah, I got it here. I rebuilt them this week. Nobody can everybody see me out there? It doesn't look like it. Freaking connections like
What happened? They dried out of water?
no. What happened was the copper that I had for the anode, they oxidized so badly it just killed them. So
You
I
heated
took
it
them.
up?
So what I did was I took them out and I put aluminum foil in it, and it fired right back up again.
You switched the copper for aluminum.
Yeah. So
Carbon is your cathode or whatever?
anode, and the
Anode,
cathode
sorry.
is the aluminum. Yeah. So they're putting out almost an amp of current, and fully charged. These are putting out almost 6 volts. The 4 cells.
6 watts. That's 6 watts right there.
Yeah. And yeah, so I'm gonna leave them. I'm gonna leave them.
All you
for a
need is
month.
water, huh?
Not even that. I'm gonna let them dry completely out. I'm gonna dry them.
I mean, if you're like out in the wilderness stuck with no power,
yeah, like well, see,
you're
these
gonna
are
find
kind of,
some water and you pee in there.
yeah, like not even that. You just stick them in the ground.
Start your phone.
Stick them in the ground, right? So you stick them in the ground. You got the natural moisture of the ground.
Great
And-
survival tool to get lost
Yeah.
out in the boonies. You put a light on that, keep it running at night.
Yeah.
Yeah.
Anybody flying over will see you.
Like this. Hold on a sec. I'll get an LED. I want to show you how bright the light is with this. Give me 1 sec.
There's garbage all over the world. You can find aluminum foil anywhere, or a piece of copper, and then all you need from there is some rock, and some plastic, like something.
Yeah, actually,
or paper even.
for my vortex, I have metal sticks, and I was trying conductive glue, and man, it was not working at all. It's like, yeah, geez, it was not only not working, but it was going in fire. It was blowing up in fire. So don't buy don't buy any conductive glue that doesn't work. So I use foil instead. Well, my lab assistant told me to
You were
use
using
foil
conductive glue to separate the two.
to stick the metal plate to the wall of the vortex,
Oh,
because I needed, I need to stick the metal plate here to the metallic wall, the zirconium wall of the vortex. So I did buy some glue, conductive glue, and that didn't work at all. So I use foil. Foil is extremely conductive, and
did you ever draw out your design on paper, like a diagram
well, yeah, it's I have 3D models of it.
on your website?
No, not on my website, but I can. I can. I don't know if I can post pictures
You
here.
don't want to put the diagram. Is that what it is?
Yeah. It's probably. I mean, it's a vortex. It's really simple, but all the technical details. It's it's complicated. It seems easy, but it's pretty complicated. So there's a lot of it. It's not the idea that you can't patent this idea because it's very simple, but you can patent how you made it.
I mean, you can't publish it. You mean?
Yeah, I mean, I have no need to publish it. I'm sharing the results already, but I'm not going to publish all the little details.
Right. Conductive
So,
glue.
yeah,
I heard
conductive
about that
glue.
stuff. I don't know why anyone would use it.
Yeah, I got it right here. I'll show it to you.
What would you want to conduct through the glue?
See, it's two type of materials, two types of glue that you mix together, and it's supposed to be conductive, but it's not working well at all. Or
And why did you need glue? Why didn't you use a piece of wire to do conductivity? Why the glue?
because I wanted the metal stick to be glued to the zirconium ring.
Light.
And you couldn't weld it or solder or
Yeah, well, I
They're not
have
bright
a
enough items.
lead. I have a welder and I have lead, but it just doesn't stick to.
stick.
It's
Do
not
you use
sticking well.
rosin? Do you using the rosin to get it to stick or sand it? None of
Rosin,
that.
what is that?
I don't know what you're trying to bind here. Two metals?
Yeah, one sec.
There's the light. You can see how bright it is.
See
Yeah, no, that's a
that's the wall, the zirconium wall right here.
uh,
I was trying to stick the metal rod to the external side of the wall here.
to
You know what I
get your
mean?
voltage transmission or something.
Yeah, to get the current going. So I wanted to stick one in the inside of the ring and another one on the outside of the
Yeah,
ring.
that conductive glue, I don't think it's designed for that kind of amperage. You're pushing like hundreds of amps, right?
Yeah, 120 amps.
I don't think that glue can handle that.
Oh,
It
yeah, so
fried, it burned up.
that was too much for the glue.
Yeah. No,
Yeah,
yeah, it can't handle that.
yeah.
It's just like it's conductive, but not that conductive.
Oh, yeah. I see. Yeah, thanks for letting me know. It
Rumors
was,
online.
I heard of that glue. I don't remember what it was, why they were making it or what it was used for, but I've heard of it before. Conductive glue. Just never used it or nothing.
yeah, it just doesn't stick well and it doesn't work well. So don't even don't and I don't recommend it to anybody.
So what is zirconium? Is you're trying to bind zirconium as one metal to another metal, which is iron.
Um, yeah, some sort of scalp, some I bought some scalp from some kitchen store, you know, and I tried to put the electrodes, the red and the black electrodes directly on um, the middle the middle sticks, but it's not conductive. It was not conductive. Even the middle sticks that I was using was not even conductive enough. So I had to wrap. We had to wrap them up with aluminum foil. Aluminum is very conductive, so it saved the day really. But that was the idea of the my lab assistant. So it was very smart. So um, he
I
told me
guess if you
to.
could weld it, you would.
Yeah, welding it's not sticking very well with the. I did try to weld it before with lead, but it's not sticking to the
You mean
it's not
solder, regular
sticking.
solder, solder? You mean solder?
Yeah,
The wire. Are you
yeah.
using the rosin, the little paste? Because if you don't use
Just
that paste, you're not going to stick. It's not going to bind. And
yeah.
especially if they're two different metals, you're going to need that paste. It's like a yellow paste,
Oh, okay. No, I
rosin
was not
paste.
using that.
Yeah, it's called rosin.
Okay,
It's what you
rosin.
use to make the solder stick.
Yeah.
Okay,
You
Yeah,
got
it
to
comes
use
in.
that.
It comes in a
okay.
little tin. I actually have some. It
Yeah.
comes in a little tin. It looks like
And in your
Vaseline.
case, just I would put a bunch of it on that area of the metal after you sand the metal, really, make it coarse, the metal that
Okay.
you're trying to bind,
It
and
looks like
and put
Vaseline.
that paste on there nice and thick and heat up your solder. Get a really hot solder iron. You're going to need a really good one
Yeah.
because the
Okay.
metal you're trying to solder to is a big piece of mass, so you need to get really hot.
Yeah.
Oh, okay. Interesting.
Yeah.
Thanks.
It looks like Vaseline. The rosin.
Oh
Try
yeah.
to get a high wattage solder iron. You know,
Interesting.
There's the
50
light from the
watts. I don't know what the highest one. They got like 100 watts or something like that.
this thing gives off.
And the
a
thing
lot.
about
Rosin.
those soldering irons, you get them that hot, you want to clean it right away after you do each solder with, scrape it clean with the Brillo or whatever, because and turn it off because the heat will damage your tip right, in no time. Those high heat solder irons, but that's what you need, and you need the rosin paste. There's a lot of that on the 2 points that you're going to bind,
Oh, thanks
and you
for letting me know.
and you want to what's it called? They call it tin. You want to if you're not you're trying to bind two pieces of metal, so yeah, you want to tin those two pieces of metal with rosin, and basically before you even try to bind the two pieces of metal, get a blob of solder, bound to the metal by itself, and once you see that you got a blob on there bound to that metal, then stick the two blobs of the two metals together and heat them up at that point, and bing, perfect
Yeah.
solder.
Wow.
Uh, you know what I'm saying? You got one piece of metal, put some of that paste on there,
Yeah.
and solder, heat up the gun and get some solder sticking on there. Get a nice blob of solder on there and make sure and so you can see that it's stuck really well to the metal. And then
Yeah.
do your other piece of metal the same way, and then stick the two blobs together and heat
Well,
them up,
they're
and
hot.
they'll bind like no problem. Bing, and pull your solder out,
Oh,
and they're
cool.
good to go. But
Cool.
you're gonna
Thanks.
need like at least 100-watt solder gun, sounds like, because that device is like at least a foot diameter, no?
150 watt iron for
Yeah.
sure.
I would go with the highest wattage solder gun you can find.
Yeah.
They're, budget, keep your budget, within your budget, try not to. There's really expensive solder guns out there. They can be up to $300, but you don't need that. You need something around, maybe a $50 solder gun to get you around about 100 watts. I think 100 watts is what you need, because I'm using a 30-watt now, and that's good enough for doing like small circuitry, But when you want to do bigger solders, you want to get at least 100 watts,
Yeah. I
maybe
see.
150,
Makes life
right?
easier.
150 watts. They
Yeah.
have
I
300 and
just
500 watt solder guns too, but
Yeah, I just have a small one for lead, and that's all I have right now. But
Yeah, I gotta get a
Yeah,
better
that's a typical problem that technicians have is getting good solder joint
yeah.
soldering points. It's really
okay,
Yeah,
difficult.
also clean it too. Like take a piece of
Probably
sandpaper
the
or
hardest
whatever
part of the whole
and sand
project,
it
you know.
because you want to deoxidize that copper or whatever
And then you got to.
material.
Sorry, Mike.
Yeah, you gotta clean it off too. But you're doing it with what do you want to solder the gallium or like a connection to it or
There's
it's
zirconium to the MHD hole, I believe, so
yeah,
okay,
that his terminal he can connect his high voltage terminal right
right?
yeah,
there.
exactly.
And keep in mind though, your solder points are going to get really hot from your amperage, and you might melt your solder just from sending amps through there. So make sure you get a nice amount of solder on there, a big ball of solder, because it's going to get hot. So
Yeah,
the more, you know what I mean, the bigger the ball of solder, the more heat it can handle before it melts.
yeah,
So keep that in mind. You're going to send 200 amps through there. That solder joint might also melt, even if you accomplish it after hook your power to it.
okay,
If
yeah,
it's not enough, if you're not making a good enough connection point and enough surface area, make sure you got a large surface area to handle that amperage transfer on that
Yeah,
solder joint.
okay.
I would say at least a half an inch. If for 200 amps, you want about a half an inch half an inch diameter of solder,
you know what? I'm even thinking
1 centimeter
You know what? I'm thinking you might
at
have to
least.
bolt it down because that's a lot of amperage, man. I don't know if the solder can handle
200 amps at what, 12 volts, 24?
that's gonna create a lot of heat on it. I'm just wondering if
That's at 10 volts. It's 2,000 watts at 10 volts. So
that's how much the
you're
solder
already
can
at the
handle.
breaker. You're already going to trip a breaker right there at 2,000 watts.
Yeah, yeah,
Yeah,
Well, if you go over 2,000 watts, you're getting close to. You're going to start heating up the plug in
solder.
the wall.
yeah,
Yeah, cause the
So
power
200
outage.
amps. Yeah. I mean, just for a short burst, it's not going to heat up give you a problem with your electric at your house. But if you
but
leave it running 200 amps
Yeah,
continuous,
if Montreal goes
I don't.
into a blackout, we know who it is.
Yeah.
yeah, I'm the one to blame.
Yeah,
Let's just say 200 amps for 10 minutes will burn the plug in the wall. It'll
yeah,
burn out.
because most homes only have 100 amp service, right? So if you pull 200 amps out of 100 amp service, yeah, that could
Well,
do
he's pulling
damage.
200 amps at a lower voltage than the grid,
Yeah, but
so the wattage is still workable.
think so. I think it'll still create a lot
I
of
mean, if
heat.
you're pulling 200 amps at 240 volts, or I don't know what it is in Canada, is it 240 over there?
No, it's 120,
120?
120 volt at 100 amp usually. Some
So
people
that's
do.
like that's a thousand
No,
watts.
I think
Yeah,
it's 30 amps, 30 amps, and the oven is 60 amps.
yeah, yeah. We run the
Something.
same as the U.S. We're identical to the U.S. in power.
Yeah,
Europe is different. Europe is 220 or 240 at 50 hertz. But U.S. and Canada, we're pretty much the same. No different.
yeah. Europe is different though.
Yeah, they run at 50 hertz, double the voltage.
12,000 watts. Sorry, 100 amps through 120 volts is 12,000 watts.
Yeah, that's a lot.
That will burn out the plug on your wall
Yeah.
in like a minute.
Oh yeah. That's
Yeah,
what I'm saying. That's what I'm saying. You got a 100 amp service
So
box.
he's not pulling 12,000 watts because he's not using 120 volts.
Yeah, but the current still is going to generate the heat regardless. You know, you could do it short bursts, but I wouldn't do it for 10, 20 minutes. You're still going to generate some heat there.
Yeah, that's what he's doing. He's doing short bursts just to do the test.
Yeah, you should be okay, I think.
Yeah.
But like a lot of people in Ontario now, because they're electric cars, people buy their Teslas. They have to upgrade their house supply to 200 amp. So they got to pull an extra main from the outside on the street, bring it in as a second line. So instead of having one line that's 200 amp, they bring two lines in, 120 volts at 100 amp. It's a dual channel. There's like a green box outside the house. They have to pull another line in from there to the house, and then they put in a splitter box outside of the house.
But the amps is never stable because it depends on the resistance.
Yeah.
So the voltage is stable, but it really depends on the resistance. So depending on the how much the what is the fluctuation of the resistance, then you're gonna get X amps.
What Todd here says is pretty accurate. You know, if you would use whatever size wire you would use to bind these two metals, that would need to be the same size of solder joint that you would need to create.
Yeah.
So if you were going to use like a wire that's 1 inch thick, your solder joint should be 1 inch.
Oh, interesting.
Yeah.
Because it needs to handle that amps.
The wires all come with the amperage rating anyway, so you should be following those parameters, right?
And for 200 amps at 12 volts, that's like 2,000 watts. If you're using
Yeah.
424
Yeah,
volts,
if
you're
you're
looking
pulling
at
that, you
4,000
probably
watts.
need to go down to like a 2 or even a 1 gauge wire, which is really thick.
2 watt, 1 watt.
A 1 gauge wire, 2 gauge wire. You have to go that thick because you're pulling that amount of current. Even like
And copper can handle more amps without getting as hot as aluminum. Aluminum
Aluminum's
is not as
pretty
good.
much been removed now. Like in the homes and that, back in the 50s and 60s, they started switching all over to copper because too many house fires. They failed.
I know exactly how those fires were happening too, because I serviced somebody that had aluminum feeds to their panel, and their lugs were tight, but the aluminum wire was loose.
Yeah.
And their house was flickering, their whole house. All I did was tighten them down, and I said, eventually you got to replace these two wires because they're aluminum. They're going to get loose again.
Yeah.
Copper doesn't do that. It holds the tension. Aluminum seems to shrink or something.
Yeah, it's
Once
Oh,
you
it
tighten the
dilates?
lugs on it,
It
over a
dilates.
few years, it gets loose.
It dilates.
Yeah, I don't know. It just doesn't hold. It doesn't hold its.
Okay.
Just doesn't, for whatever reason, they get loose. You could tighten them again, and in a few years, maybe the vibration, or I don't know what it is, but
I'm just
the
gonna
lugs
step
don't
away.
don't
just
hold
gonna
the
step away
aluminum
for,
that long.
I'm just gonna step away quick for a smoke. I'll be right back, guys. Just carry on.
Okay.
And I never saw anything going on while I was there until I got to the panel, and then I was in the panel, and it was daylight, so it's hard to see any sparks. But I turned everything off, and I saw a spark coming from around the lug area where the main lines come in, and I was
Yeah.
like, "What's going on there?" And I checked the wire; it was loose. So, and I said, "Oh, it's aluminum." And I remembered another electrician mentioned something that to me. I was working with him in the field. He said, these aluminum wires, they don't hold their tautness with the lugs, and they get loose over time.
Oh, so
Yeah.
they make wires using aluminum because they're just cheaper, I guess.
It's lighter. They're lighter, so it's easier to carry and install.
But is it cheaper? Too?
It's cheaper too, I think. Yeah, it's cheaper and lighter. And the fact that I think that it's lighter is why they made it, because it's like you can set up an electrical system really fast.
Yeah, but the temperature is not
Right, they don't hold the heat that well.
fluctuating. The temperature is not fluctuating a lot in Florida, so they shouldn't dilate that much. You know what I mean?
I don't know if it's a temperature thing. I think it's something to do with the metal. It just doesn't hold its tautness. Yeah,
Yeah.
it's weird.
Yeah.
So it won't. You can screw it down with a lug and tighten the lug on that aluminum wire and bolt it down and everything. But over like years will go by and somehow it'll just be loose, slightly loose. And you can tell it's just both of them are like so loose because there's two phases,
Okay.
and they're just like ever so slightly loose, and you go to tighten the lug, and it's like it just makes an indentation into the aluminum. It's softer metal, I think, is what it is.
Okay.
So copper is harder metal, so the lugs they hold the
Yeah.
wire, but the aluminum's softer, so when you tighten it, it makes a pushes in the wire very easily.
Yeah.
It just creates that problem. It's a hazard, and that's why the house fires were happening. Because when your main lugs are loose inside your panel, that's a hazard.
Oh yeah. See. Yeah, that makes sense.
It'll get sparks and fire,
Okay.
and it heats up. The aluminum wire will heat up and light up on fire
Oh,
because
they heat up more easily.
right. Well, and because people would not know how to rate the aluminum to the copper on the amps. Copper can handle more amps with the same amount of thickness.
Yeah.
So, and installers would go ahead and probably install the aluminum on a 200 amp panel with the same thickness wire of aluminum, but this is aluminum now. It can't handle 200 amps. So then people would pull 200 amps on their panel through an aluminum wire, and it would fry because it just gets too hot, and it's not designed to handle that much heat. Just like
Interesting.
solder. So if you're buying solder, then you want to also make sure the solder you buy can handle high heat, high temperature solder, because they have that. It's just different alloy.
Yeah.
Which means you're going to need a higher temperature gun to melt it, which is good because when you send your high amps through there, your solder joints won't melt or get too hot. They'll be able to
Yeah.
handle it. I believe they have high temperature solder too.
Oh, cool. But it's all. Well, I guess the aluminum would be better if it was larger. It could handle more current. But the question is, if you have to double the aluminum, then you might as well buy copper for the price.
Copper, right? Because it can handle more heat than the aluminum can.
But overall, if you have a larger aluminum wire, it's gonna be the same price for a thinner copper wire for the same amount of current it can handle.
Right. So like a copper wire that's slightly thinner than aluminum can handle the same amount of amps before
Yeah,
it burns up
yeah,
as
yeah,
the aluminum can.
yeah,
So the aluminum needs to be thicker. It has a different kind of eddy current it has eddy currents like aluminum, and so does
right.
copper. So if you notice, like copper, when you pass a magnet by it, it seems to uh, have more braking effect on the magnet than aluminum does. But for whatever reason, the
Yeah,
aluminum heats up. Yeah. Well, the aluminum will melt before the copper.
yeah,
Maybe that's got to do with the melting temperature of the two metals. I don't know if they're coordinated like that. Possibly.
yeah. Oh, I forgot to say that with my technology, with my theory, that seems to slowly being confirmed with experiments. Then I can do the anti-gravity energy teleportation, uh, tractor beams and force fields. Tractor beams being kind of you it induced time dilation, So everything within the high energy beam will induce time dilation, which will freeze whatever's inside that beam, which is the same thing with the force field, but the force field is more like a scattered wave, whereas a tractor beam is a direct beam. And the energy teleportation, I think I said that before, is just a matter of converting back and forth the energy into lower frequency but of higher energy density back and forth. So that's how you teleport energy. So I think that's pretty cool. It's a cool technology. It's not, but the tractor beam will require. I made the calculation. The tractor beam would require 1 times 10 to the 16 times the world's most powerful laser. So it would require a lot of energy, but it's possible. Just to let you know that tractor beams, force fields, and energy teleportation is not science fiction anymore.
It's true.
Does the tractor beam tie in with the MHD somehow?
Yeah, because it has to do with energy density that induces acceleration, time dilation, and temperature change. So
The MH,
the MHD, what I showed, it induced acceleration, but it also, if I had a clock, you would see the clock being slowed down or speeded up. I
so
should be slowed
you
down.
believe that the anti-gravity effect of the MHD is an acceleration going on? It's not like
Yeah,
a polarization thing. It's a momentum thing.
it's I'm changing the acceleration. The gravito-electromagnetic field has an acceleration and has a direction.
Hmm. It does.
But the direction, I need to review that because I was expecting. Remember, I was expecting a weight loss and all that, and if you change a clockwise, counterclockwise direction, so that's what I was expecting. But if it's sideways, then I get what I wanted to have. So I need to redo the experiment with the vortex sideways.
I mean, the centrifugal force will. I mean, my reasoning for this whole thing is when you pull your legs in on the spinning chair, you go faster because you got lighter. You got lighter. Somehow you were heavier with your legs out.
Yeah.
And when you pulled your legs in, your
Less
weight
surface area.
reduced.
Less surface area.
Because you're spinning
Oh, yeah, maybe
faster,
this one.
and you can also feel at the same time that you're also sitting up straighter when that happens. That's because you got a little lighter, just a tiny bit, and your body can sense it. And you sit up like that because you feel the lift in your whole body, not just in your legs. You feel it happening in your whole body, and you have to pull in, evenly to get the maximum result for some reason. I just have a pickle about figuring that out, man.
Yeah.
That whole centrifugal effect, you know. And we're a charged body of mass, also. But you could put anything in the chair, a stick, and with a remote controlled lever to pull the stick in, and you get the same effect. I'm pretty sure it's a mass thing.
Yeah. So
The spinning mass effect.
yeah. So that then induces acceleration, time dilation, and temperature change. So, but time dilation, I don't know how to measure it other than using
On the
a
output.
sun timer.
Well, Bruce De Palma, when he did it with his machine, you have to do it on the axis. So if it's spinning like this, the axis point there, you have to put the clock right above the axis.
Yeah, but the problem is I'm emitting a strong magnetic field, so it affects the clock, you know.
Apparently, he says when
Mm.
he did his, because his was actually set up in a box in a chamber, and still, when he put it on the longitudinal axis of the spinning mass, he got time dilation. Did it with digital as well as analog, and he got the same effect.
Interesting.
Hmm.
Without
It's hard to conceptual. It's hard for the mind to accept that time is that weak of a force, and
but
it's almost like
time,
time is as weak as gravity.
yeah, but
You could jump.
the problem with time is people, because of general relativity, mass, people think we can go back in time, but we cannot. Time is not a
Well, for
the,
some
the,
reason,
the,
we're able to slow it down by
yeah,
spinning a
yeah.
mass. You
We can
can't
slow
stop
it
it or
down.
reverse it, but you seem to be able to slow it down.
It's like temperature. It's an absolute variable. You know, you can speed it up and slow it down.
It's almost
But
like it's a river of
yeah, but
flowing
you
water
cannot
that you can
you
put your
cannot.
hand in it and slow it down.
Yeah, but there's no negative time. You know, it's like
Right,
temperature.
you
There's
can't
no
stop the
negative
river. You can't
temperature.
stop the river, but you can put your hand in it and
Yeah,
slow down
exactly.
some of that water.
Yeah, exactly. So that's the. So if you think about time being just something you can slow down and speed up, then it's much easier to conceptualize. You know, it's just something that the cohesion
Yes.
of the atomic molecular cohesion is slowing down and speeding up. So for some reason, relative to the energy density, then it's very easy to visualize.
It's almost like the rotational speed of the Earth is dictating our lifespan based on the RPMs or something,
Yeah,
and its impact on time or something.
yeah, exactly.
Yeah. What
So
if the Earth was spinning faster? Would we age slower?
Good
You know,
question. That's a good question.
uh, well,
maybe in the past the Earth was smaller, it had less mass, and it was spinning faster, but in proportion to its spin now and its mass then, it was still slowing down time, or at least the aging process more.
but I did hear that the Earth is slowing down.
Right,
The
ever
Earth's
so
spin
slightly.
is slowing down.
So say
Well,
65
it would
million
have to
years
because
ago.
it's growing. What's that theory that they have? They
Because
have a
of the
name for it.
moon, I think. I
The
think it's because of the moon.
the
Well,
growing.
they
It's
said,
called growing Earth theory. You know what I'm talking about?
yeah,
It's,
I think it's slowing down, but at a very, very tiny rate. Like, say 65 million years ago, the daylight hours were a lot shorter because the Earth was spinning faster. So instead of a 24 hours in the day, might have been only 18 hours because we were spinning faster, right?
hmm.
So over a long period of time, 65 plus million, maybe 100 million years ago, the Earth was spinning at a faster rate than what we are now today. So, say a million years or 100 million years down the road, our one day might now be 48 hours long
Or is it the
in one
sun?
day.
Or is it the sun creating our time? You know, or both, the sun and the Earth. They're working together to create our time frequency. The sun is a spinning mass.
Yeah,
It's a plasma ball.
yeah. It's
It.
It's hollow. The sun's hollow.
Whatever it is, it's definitely some type of energy. It's an energy of sorts. And energy is spinning. Is always it's doing some kind of a spin motion.
Yeah.
if not left or right or whatever, it's spinning, you know. And that's
Well,
all you need.
it's moving along with the galaxy, right? Our galaxy is moving through the universe because they're saying in another 100 million years, our galaxy is going to collide with Andromeda. We're actually going to intertwine with another galaxy. Now, that could be catastrophic for us because if another celestial body from another galaxy is now in our proximity, and that
Yeah, well, hopefully by then we'll figure out the UFO, you know, ships and things like that.
I'm not too worried about it. I don't think I'm going to be around in
I think we can do that in a million years, you know.
I'll be long gone. I'll be a fossil by then. So.
Let's just say if we don't figure out how to be badass pilots like these aliens that are flying around up there, or mysterious Earthlings with ships that we wish we had, whatever they are flying around up there. If we don't figure this out within a million years, we don't deserve to be here. It's just too much time gone by there. You had your chance. Time to go. Next. You know?
Yeah.
It's been a million years, man. You ain't figured it out in a million years, you know. It's been 100 years, and look what we figured out with electricity. So I think we'll do it, you know. I think we'll figure it out. I think we probably already have.
So just to show everybody, I got my battery going here. I got the light. You can see how bright it is.
It's like proprietary.
I got it hooked up to the cell. So yeah, I'm going to let this battery cell go for as long as it could go. Charged the capacitor bank up several times already. I was telling Philip earlier tonight before we went on that as soon as you take the load off the battery recovers. So yeah, you could pull it down. You could charge a capacitor bank, which is basically almost like a dead short. It's very hard on the battery. As soon as you take it off the capacitor bank, the battery,
you know, it's a fuel cell, right?
Up. Yeah, yeah.
Yeah, you should sell that stuff, man. It's like
yeah, well, it's way better than the original version, like the one that Laser Saber made. And he made a good battery that would kind of inspired me using the magnesium. So I've kind of refined it. So now I'm 3D printing these cases, and they go together. They're very, very tight tolerance. And when you put the anode and cathode in on both sides, the gap between the anode and cathode and the solid state electrolyte that I'm putting in the middle is about 3 millimeters. Plus the surface area, it's giving me a huge amount of current. And these things are pumping out. Each cell can give about 1 amp of current. So
each cell, well, 1 amp at 1.5 volts.
Yeah, but if it gets pulled down by like a big load, then you know the voltage obviously drops in the battery. But the second you take the load off, it just recovers. It comes right back. But it's enough to charge capacitor banks, and capacitor banks are very hard to charge. Actually, they're really bad to use a battery to charge up a capacitor bank. It kills a battery because you're pulling amps off the battery. But it doesn't really have an effect on these guys. Since you disconnect it, these things go right back up to their running voltage, which is about 1.6 to 1.8 volts. So they're pretty durable. So I'm going to let these sit, completely dry out completely, and we'll see where we're at in about 30 days from now, how much power these things still have. But if it only takes a couple drops of water to, reactivate them, hey, that's not bad. Or the original design was like this double field battery, coil,
copper and iron.
Just stick it right in the ground, and the natural moisture of the ground will keep these things running all day long. You can put stacks of these in your backyard. You can ride all your outside lights in your backyard for free.
Well, I mean, as long as the two opposing metals aren't fully corroded, and they eat each other apart, they biodegrade.
I'm using aluminum.
It takes years, though.
Carbon graphite, right? So I'm using aluminum and carbon graphite. They don't corrode. They don't oxidize, which is great. So that means they're going to last a lot longer.
The aluminum will take a long time, but it will.
Probably would take a very long time.
At
But
least
from what I checked
10
on the chart, they
years.
say they don't really well, 10 years is pretty good. How many
Yeah, I
battery?
know.
How many? How many batteries?
10
Not
years
gonna
of,
have
of,
10
of
years.
using the power as well,
Yeah,
hydrating it over and over.
like totally worth the investment for sure. And
It's
they didn't.
it's it's the best source of free energy you can get in an
Yep.
emergency, you know.
But yeah, let's expand on this a little bit. So now I got this power cell. It puts out power all day long. I could hook this up to a jewel thief or a jewel bringer, and I could run a whole whack of lights using this. And then you can use the jewel bringer to run a whole bunch of lights, for your outdoors
Mm.
or patio or whatever. Just have these stuck in the garden. Have 3 or 4 of these banks all
Well, what
linked
the
up
jewel
together.
ringer does, the jewel ringer just takes a really like a 0.2 volts, and it
Jacks
just
it up. Jacks it
yeah,
up.
it creates a flyback.
Right, exactly. So you do that, you can hook up, 20, 30 lights.
Yeah, but you're still gonna have the same wattage that's in that dead battery or that 0.2 volt battery,
Yeah.
you know. But
But
if you got a good battery, then you're gonna have more watts in there.
that's right.
So
You'll be able to drive it for a longer period of time. Hook a toggle switch up to it and you can shut it off when you're not using it, or a light sensor so at nighttime they'll turn on automatically. You're laughing.
So Mike, I changed my course with the flyback capture setup. I decided not to do the comparator thing, Bedini's comparator thing.
Right.
How he dumps the flyback into a capacitor, lets the amps build in there and the voltage around
Right.
50 volts or whatever, and then he hits the battery. I am going to do this another way because I believe that when you drop the voltage, you lose efficiency of transfer. So by dropping the flyback voltage, you're losing efficiency of transfer to the battery. So I'm going to keep the high voltage flyback.
Yeah.
I'm going to send it back to the battery, and I'm going to close a switch to charge my capacitor bank. Just briefly charge the capacitor bank, open the switch again,
Yeah.
and let the capacitor bank run the flyback.
Yeah.
And never convert the flyback until it hits the battery. Just straight to the battery.
Yeah.
Because it's high voltage.
Yeah. And all it needs is that pulse.
Well, I did the comparator thing. I dumped the flyback to the capacitor, then I went from the capacitor to the battery, and that kept a higher resting voltage over the battery while it was running, which was impressive to say the least. But it did not keep the battery from draining overnight. It still had the same thing. So what it was I'm assuming that when I'm dumping the flyback to the capacitor, lowering my voltage right there, then I just lost the transfer efficiency.
Yeah.
Because I dropped the voltage.
Yeah, I did
If you keep that high voltage spike and you snap the battery with it, even though the fact that it's such a small amount of current tells me that all of that little bitty current is going to get in that battery. And I mean all of it. Why all of it? Because it's a really high pressure and a very small amount of juice that you need to send in there. But if you dump that little bit of juice and that high pressure over time into a capacitor and convert those little pulses into a bigger pile of energy with a lower voltage, the fact that you dropped your voltage and have more energy does not mean you're going to have higher efficiency in transfer. The transfer comes from the potential, not the amps.
Yeah.
So that's my reasoning behind not doing the comparator, and I don't agree with it because I don't think it's the way to do it. I firmly believe you just use the capacitors to run the flyback driver and dump the flyback straight to the battery.
Yeah.
Do not
See, I
dump
did
it to a capacitor.
I did an interesting thing. So what I did was, the big 60 volt 16,000 microfarad capacitor.
I know.
Okay, so what I did was
Hi.
today I tried to. Hey, Lulu,
Hi, everyone.
welcome to the show. Yeah, so what I did was I took that power that was coming off that capacitor and patched it right back into at the point of my circuit where it's after the spark gap and after the diode. So what happened is when I did that, I was able to back off on the battery input by 50%. So I was only using 25% of the battery input, and it was sustaining the speed and sustaining the power in the capacitor at the same time. So I was looping it right back, and
You
that
were
was
not, were you dumping the flyback to the capacitor or straight to the battery?
no, I was dumping it right back, right where the coil is, right back into the coil.
Oh, okay, yeah.
So
That's,
when
I
I
don't
did
agree with that
that,
either.
but here's the thing: when I was able to do that, now I could turn my speed controller from 100% down to 25%,
Yeah,
and it kept sustained its speed.
right. If you could convert that flyback straight to locomotion 100%, then
Well,
you're not going to lose
instead,
any of it, you know?
so
I
technically,
just
like
think the
I have,
battery's more effective.
well, it is, but what I was doing, I was taking the strain off the battery.
Because
So
the
it,
locomotion devices, they're not so tuned to the flyback. So it's like getting the locomotion to harness that flyback, all of it. It's not really tuned to that, like the battery is. And but these locomotive devices, they're more tuned to the battery. So they're going to
yeah,
harness the more efficiently the battery voltage than the flyback voltage.
yeah.
It's just not
So
their tuning. The
I,
coils in those motors are not tuned for high voltage.
yeah,
If you want to turn the flyback straight to locomotion, your motor has to have a high voltage winding on it.
yeah, you have to have a lot, and that's why my coils are minimum 1 pound.
And
I
typically
actually,
motors don't have high voltage windings on them. So any
right.
motor that you're
So
trying to,
yeah, so what I'm thinking of doing next is switching that 1 pound coil to a 2 pound coil, and
and
that
once you
way,
dump the flyback into the coil, you're using that to turn it into locomotion.
right, it converts it back into locomotion, and then it just repeats the process over and over and over. And because of that, I could actually almost to the point where I can disconnect the battery completely and
Well,
make it a
let's just say
solid
if it's a
rubber.
900-volt flyback, then the coil would have to have as many turns as it would take to create a 900-volt step-up transformer
Well, the highest I
from whatever
recorded,
voltage you're creating the flyback to.
right, the highest high voltage I created with this one particularly was about 560 volts. That's
So your
the
coil needs to be able to have the winds for that,
right.
at
So
minimum, if not a few more
that's
turns.
yeah. So I got 1 pound in there now. I'm thinking I might want to go to 2 pounds.
Right.
So because if you go by Newman's principle, it's energy to mass. As soon as you put power or high voltage to a large mass, especially if it's copper or iron wire, that's where the electrons are settling in the mass.
The
As soon
problem
as you
with
hit it,
turning this high voltage into locomotion is there's no current behind it. I mean,
well,
there is, but it's like minimal.
well, you'll get it when it goes into the capacitor. Now, I also did something interesting this week as well. The voltage coming out of the large blue capacitor, the 60 volt, 16,000 microfarad. I did notice, well, if I put a 1K ohm resistor going to the load, my voltage in my capacitor, instead of being at 30 volts stable, it went to 40 volts stable. It increased the voltage in my capacitor, thus creating more pressure in that capacitor and giving me more output. So
Right.
after that,
You have to do whatever it takes to get that voltage up
up and
without increasing the amps with it.
right.
You know,
So
don't
yeah,
concern yourself with the amps, just the voltage, you know.
right.
Try to get rid
So
of the amps as you're increasing your voltage.
yeah, so just by adding a 1K ohm resistor really changed the amount of voltage in that capacitor. It increased it.
You had it in series, you said?
Uh, what part of the circuit?
You had a resistor in series with the capacitor.
Yes. in series.
An increase.
Yeah.
The resistor will create a voltage.
Yeah. So because I put a bottleneck on it, I squeezed the neck on it, the power increased in the capacitor by 10 volts, which
The
is great.
resistor was on your negative or on your
On the positive.
side?
On the positive.
From your source.
And it helped actually increase my output and current too. Actually increased my current.
That's strange because you would think that would limit your current.
Yeah, that's what I thought too. It increased it. You see, what I think's happening, the reason why it increased is the fact that I was bottlenecking it at the capacitor. So now I'm forcing more of a charge on the plates inside the capacitor. There's now pressure there. And that pressure has to go somewhere. So it's going to go through the resistor at any way possible, even if it has to create heat. Right? Because when you heat up a resistor, or when you put high current through a resistor, it heats up, which is normal, right? So it increased my output current as
Your
well.
resistor got hot. Oh, yeah.
It warmed up a bit, yeah.
Yeah.
It did, yeah. But
once the capacitor fills up, though, it will behave
Push.
like a open circuit.
It pushes. It pushes.
Well, it pushes on the other end, but on the end that's charging the capacitor, it's behaving like an open circuit once the capacitor is full.
Yeah.
If the capacitor is slightly empty, even just a little bit lower, like let's say your source that's feeding the capacitor is 12 volts and your capacitor drops to 11.9, the side of the capacitor that's hearing the source at 12 is going to act like a dead short, and and bring itself back up to 12. That's how efficient they are at charging.
Yeah, because my input voltage is 26
But
volts.
as soon as it hits 12 volts, it's going to act like an open circuit and no longer take charge.
Yeah. See, like that one there that I'm using is 60 volts at 16,000 microfarad. My input voltage in the system is only 26 volts. I'm getting that voltage up now to 40 volts using the 1K ohm resistor. So I've increased more than double the amount of power, almost double the amount of power that I'm putting into the system. That's what I have sitting in that capacitor on the way out.
Right. I mean, it could be a 100-volt capacitor and you're feeding it, 50 volts. As soon as the potential on the capacitor is matching the potential of your source, even if it's 50 volts and not 100, that capacitor will still act like an open circuit to the source once the potentials are matched. They're both 50-50. One's 50 volts, the other 50 volts. Now the capacitor no longer hears the battery, and all it hears is the load.
Right.
And then as soon as the load takes some of the voltage out of the capacitor, now it becomes a short again to the battery and takes power from the battery.
See, like I could hook up that really big one, the big electrolytic one, it's a 2800 volt DC at 8 microfarad. When I hook that up in the same spot where the blue capacitor is, it goes up to 121, 122 volts right away. It just boom, it fills it.
Yeah, they charge faster than they drain, way faster.
Well, it's a bigger capacitor, more mass, but less microfarad. It's only 8 microfarad, right?
Yeah.
So
I mean, originally I thought it would be better to use capacitors to capture the flyback because they charge so fast. And you think because of that, the battery is not going to capture as well as the flyback as the capacitor would, which is not true because they both capture the flyback equally, the capacitor and the battery. It just, sending energy from a capacitor to the battery is less efficient than sending energy from the flyback to the battery.
Yeah.
So I just think you're losing power when you go from the flyback to the capacitor and then from the capacitor to the battery. There's a loss there.
Well, I'm not putting it right back to the battery. I'm putting it back into the motor.
No, I mean, not you. I mean, in general, like
Yeah,
the
in
Dini
general,
comparator
yeah.
circuit or whatever,
Oh
people
yeah,
that are
since you
doing
do
that.
that, since you do that,
I firmly believe that there's a loss there because you're stepping down the voltage for one,
yeah,
and that's you have less voltage potential to now push into the battery than you
yeah.
did when it was a flyback volt.
So the way I did it today,
Originally, I didn't think that way. I've changed my mind recently. I mean,
yeah. Well, the way I did it today, when I patched it back directly back into the coil, it recycled it, and I was able to back off on the amount of battery input. I was actually able to turn
right.
it down to 25%, and the motor was still speeding up. It was sustaining itself.
If your
So
timing's right, the coil will. Yeah.
yeah,
I
because I
mean,
know the
it's kind of
flyback
hard though,
way.
but
I know the flyback is way exceeding the amount of power input.
you're feeding it into a secondary coil, right?
No, I'm feeding it back into the same coil that's running the whole system.
I
Same
think
coil.
when you do that though, you're gonna have like won't it like just like
No, because I put it through the isolation transformer that breaks the symmetry. Then I put it through the full wave bridge to the capacitor, and from the capacitor back to the motor. It doesn't recognize that power anymore. Because normally, if you just hooked it and just looped it, it would short itself out.
oh, so you're not directly looping back to the coil. You
No,
have
you have to
something in the
break.
middle.
Yeah, you have to break the symmetry. So I've
Oh,
done that.
so I see the flyback from the first coil. You're sending it to a transformer before it gets used again. Okay.
Isolation transformer. You have to break the symmetry. If you don't do
Hmm.
that, if you just loop it
And that would
back
take
down,
some time. That would take some time, right? To
so
go through
if
the
you don't,
transformer, then the rectifier. By that time, you can
yeah,
use it. Right.
if you don't do that, it will short itself right out right away. It will kill the entire motor right there on the spot, dead horse.
I thought you were using it to drive another magnet on the rotor or something.
No, I'm feeding it directly right back in where it came from.
Right. Yeah, you could do that too. I don't see why not. I mean,
As long as
just
all,
that's
all
just
you
as
got
good
to,
as putting it back to the battery,
yeah, all you have to do is break the symmetry. Second you break the symmetry, you can loop it. That's where a lot of people gone wrong for so long. They say, "Oh, I'm trying to loop it," but every time I do loop it, it just kills the motor. It just dies because you haven't changed the symmetry of the power
So you're
coming
going from
out
flyback to transformer, transformer to rectifier,
yeah,
and then to the battery,
to the capacitor first.
and then the capacitor, then the battery.
Not to the battery. It's going back into the coil again. Not into the battery, into the coil. The
Okay,
drive coil that
from flyback, you're dumping it into the capacitor,
right.
and then the coil, and then the isolation transformer.
It's going okay. So from the drive coil that's running the motor, the flyback comes out. All right.
It hits your
Goes to
transformer.
goes to the isolation transformer. From there, it goes to the rectifier. From the rectifier to the capacitor. From the
Capacitor.
capacitor, I loop it right back to the same coil where it started.
And okay, and the battery keeps the capacitor going.
Yeah, but only 25% of the battery is needed after that.
Yeah. So you dump the flyback to the transformer, and then the rectifier.
Yeah, because
That's
you got
kind of the same. It's kind of the same thing as dumping it to a capacitor.
yeah, yeah. As long as you break that symmetry, and that's where I
That's
break
interesting.
it right at the isolation transformer and the rectifier. Those three components together break that symmetry of the power. So now the power going back into the system, the motor doesn't recognize that power anymore. It thinks it's coming from somewhere else.
What do you think of this setup? Using the capacitor bank to drive the flyback driver, and then sending that straight to the battery that's feeding the capacitor bank
Yeah, I could do that too,
with a switch.
but I'm getting the weird effect where now I can back off on the battery now. I don't have to use the battery as much.
I
So
like to keep the battery in the loop because it's so good at
well,
the
no, the
flyback capture.
battery, no, but what I'm showing here is I'm getting close to the point where if I keep going and advancing, in the right direction, I could almost take the batteries out of the situation completely, and it would be a self-runner.
That'd be ideal, but you're forgetting something here. Have you fully tuned the battery to flyback voltage only? I mean, have we converted a battery? Has anybody converted a battery to flyback battery to be a,
No,
because
you
these batteries are not flyback batteries. They're going
No,
to get
No,
converted.
you can't do that. No, it's a negative energy that's coming out of the coil. You can't do it. You have to convert that battery to a negative voltage battery.
That's what I'm saying. Have you done that yet before you eliminate the
You-
battery from the
and
picture?
you-
Because that's good. That's an ideal kind of scenario to have a battery
Well,
that's been
Bandini
fully
talk-
converted by negative energy in your
Yeah,
system.
because Bandini talks about that extensively. He says
That's what I want to do. I'm trying to convert a battery. I've never done it yet.
right. So what you
Successfully.
got to do is you got to drive that battery down to like 2 or 3 volts. All right. As soon as you do that, now you charge it with radiant energy. So
Right.
from now on, you only charge radiant power in that battery, not positive energy.
And you use that to run your circuit.
You use the
As your source.
positive energy. Use the positive energy to
Now,
run.
get the positive energy out of the picture.
Well, you could, but you're not supposed to, according to Bandini.
Really?
Yeah. If you go
I
to the
didn't know
energy,
that. Why
Yeah.
did he say that?
because you have to convert from the.
He's
the
sort of
hot
contradicting
energy-
himself there, because then that, he says, you want to convert this battery to a negative energy thing, And
Yeah.
why else would you do that other than making it your source?
So what he's saying is the negative energy battery, you would hook that up to an inverter and then charge the battery that's running the system using an inverter and a charger.
And what do you do with the output of that system? Send it where? Back to the battery that's
Well,
running it.
Well, no, that battery.
And
with
that's
the
a negative
energy-
battery.
Right. You use that to power an inverter that runs a charger to drive
To
that.
create positive energy to then
So-
feed back to a battery
so-
that's negative energy.
I know it sounds weird, but he explains it where the negative energy battery is what you use to run your inverter. Okay, that's the whole point.
Man.
Because the negative energy battery bounces back faster than the positive energy. It's
What did he say to charge it with? Charge it with negative
Yeah.
energy, right?
No, you have to charge it with a positive energy.
After it's been converted to a negative energy. you
No,
charge it.
it's 2 separate banks, Mike. It's 2
Oh,
separate
two banks.
2 separate banks. They're totally opposite.
So what's recharging the negative energy bank if you got to have something recharging it.
Right, the positive energy. Yeah, the positive energy runs the motor. What's getting charged is batteries with negative energy.
Negative energy.
Right. Okay. And
I said that 10 times already.
Right. But what I'm saying is you have to use positive energy to run the motor.
To
Okay.
create the negative energy. I get you.
Create negative energy. So now you got negative energy in that battery you just charged with the motor, right? Now you can hook that battery to an inverter and run your devices with it.
Right.
And then you just, because you get so much power out of that battery that's running the motor, you could probably charge that negative energy battery 5, 6, 10, 20 times before you would have to recharge the battery that's running the motor. So you're getting way more bang for your buck
Mhm.
that way. Because
So you
Yeah,
have
they-
2 batteries, one at each end.
right.
Okay.
So
One is the
positive-
one is the running battery, it runs the
One is the
system, and the
charge,
other one
yeah.
is the one that charges
Right,
off the system,
Right.
charges from the system.
exactly. And the reason for the negative charge to run an inverter is the fact that you can rebound and recharge that battery 50 times faster than you can the positive charge battery. Positive charge battery takes hours. Where the negative
But
charge
wouldn't that negatively charged or that negatively conditioned battery, if you keep charging it with a typical inverter, wouldn't that convert it back to a positive battery?
Yeah,
then?
you can do it, but it's actually very bad for the cell. It could actually destroy it. And even Rick Friedrich talks about that in some of his
So why is
lectures.
he using the inverter then? What's the inverter doing? He's running the
Run
motor?
your utilities. Run your
So-
utilities.
oh, just run your devices with it. Okay.
Yeah, your devices, your utilities, whatever you want. Battery chargers, whatever. It doesn't matter. But the fact that the negative energy is there because of the fact of the characteristics of recharge. They're way faster than your regular battery. Regular battery takes, 5 to 8 hours, where a negative charge battery could charge within 30 minutes and get the same performance, if not actually better.
I
So
think, you're right about draining the battery
you have to.
before you charge it
Yeah,
with the spike.
yeah.
Because, I wasn't doing that. And my batteries were,
Getting killed. You're destroying them.
you think so?
Yeah, you gotta drain the battery.
I mean, they weren't like getting destroyed, but they just weren't like,
They won't hold the capacitance. It loses its capacitance value. So yeah, the best thing to do is just drain that, put it like a car light up to the battery and just let it drain it.
and then spike it.
Yep. The first charge will take longer. It might take a couple hours, but as soon as you get that first good full negative charge in it, then you're good to go. Then they rebound really fast after that.
Even after you drain it, you can rebound it with a spike.
Yep. Oh yeah. Yep. That's the whole point of it, because it takes a lot less time than a
You go
regular,
below the recommended volts to do that, or?
well, just for the first time. So after that first time, you drain the battery like down to 2 volts, charge it.
Wouldn't that
back
kill
up.
a regular lead? That would totally destroy a lead acid, wouldn't it?
Nope, because you're going to put the negative charge in it. You're reprogramming
Right.
batteries.
I mean, I've seen batteries that were like already damaged like that, that just ticked off somewhere, hey, thank you for the battery. It's got like no half a volt on it. Put the spike on there and it's coming back, you couldn't do that with a regular battery charger. It would just say, oh, this battery's
No.
not good. Can't help you.
That's right. Yeah, you're basically reformatting the original battery and the original charge in it. So that's you have to listen to the video, and John Bandini talks about that. It's very important because a lot of people go wrong with it. Even Peter Linderman, he had a whole conference on that too. How to reformat these batteries properly. Because in the beginning, he was killing all his batteries. They were dying. And they're trying to figure out why. And they figure, okay, let's try to kill a brand new battery right down to 2 volts, and then recharge it with the negative energy. And then it worked. The battery stayed alive, and they were able to recharge
That's
it.
strange.
And yeah. So you're taking out all the positive ions and flipping it over to the negative ion, and basically making it into its bipolar opposite, right?
It's like changing the battery's polarity.
Yeah.
Yeah.
Yeah. Easiest, in metaphorically speaking, yeah.
You don't think like throwing the flyback into a capacitor is like a total waste of the flyback when you can be hitting a battery with it, or hitting a like a capacitor will capture the amps and all that. But
You see, like Bandini was also saying too, the dry battery is using a positive charge on it, right? So if you build your motor correctly, it should not draw more than 100 milliamps. He says if it draws more than 100 milliamps, don't even talk to me. So
you drive coil.
Yeah, your drive battery. He
Coil,
says
drive coil.
Yeah, if it pulls more than 100 milliamps off your drive battery, he says
Right.
don't even talk to me. He says it's got to be under 100 milliamps, because you're not getting good efficiency if you go above 100 milliamps. So like my motor usually sits about 50 to 60 milliamps under a load. So that's pretty good. As long as you stay within that range. Sometimes I've got it down to 20 milliamps.
You're using a resistor to do that.
No, not at all.
What's
So
the
like,
ohms on your coil again?
oh, I haven't even measured this one. I don't think they're pretty low, very low.
12 volts.
No, I'm putting, well, my drive battery is 26 volts,
26.
212, 212.
You need like 200 ohms at least
Yeah.
on your
So
coil.
I've got my motor. If I get it really tuned good, I could get it down to 20 milliamps input.
I'm going for a 150 ohm coil. That'll pull about 80 milliamps.
I think next week I'm going to try that 2-pound coil. I think it's gonna really improve because I'm gonna really, I've been watching a lot of stuff on Joseph Newman, his theory, and it's right. He's right. That's all I can say is he's right. High voltage into a large mass. That's the key. So
Oh, it's the mass, not the surface.
it's the mass.
No,
Energy.
I mean, the mass eventually translates to surface area.
It's
That's
mass.
the same thing.
Energy to mass. That's why he was getting so much power out. He was running a giant mud pump with his 7,000 pound motor. He's putting 460 volts at 50 milliamps. All the 9-volt batteries he were using, they were all dead. They were all dead batteries. He's moving a 7,000 pound rotor. Yeah, it's energy to mass. Put high voltage to a large mass, you're going to get a shit.
All you need to do to get the spike or the flyback to result is to send 1 joule through that wire. And if you can do that, you're in business. You have a super coil or super system, because if you can send 1 joule through an inductor and control it down, fine tune your circuit that well, to only send 1 joule through that coil,
the way
you're still going to get that flyback.
The way Newman explained it, and this is what I got from it. He says the energy lies within the coil itself. It's the mass, the electrons that are bound to the mass of the coil. When you hit that with high voltage, those electrons are now active. They're now moving. That creates your electromotive force. When you got electromotive force, you got power. He says everybody thinks it's coming from the power. No, the power.
When you send that 1 joule through the wire, you're aligning all the molecules in the same direction, which then gives you your magnetic field.
You're triggering the power that's already in the mass.
You're turning the molecules to all face the same direction. Is what you're doing. They're already there. The molecules are there.
You're polarizing. Yeah.
That in turn creates a magnetic field in the wire.
Yeah. Electromotive force.
But all you need to do to get those molecules of copper to all face the same direction is to send 1 joule through it.
Right.
Just 1 joule, not 2, not 3, 1. It only takes 1 joule. And does that joule get from one end of the wire to the other end of the wire? That all depends on the voltage now.
It's just
not the amps, the voltage.
Yeah. That's why all his 9-volt batteries were all dead. They're all
right.
dead batteries.
But he wanted the voltage to get up high to make sure you can get at least 1 joule through that wire to get the effect. And that wire was very thin. I believe it was Litz wire.
Yeah.
What did he use?
Yeah, he was using Litz wire. Yeah.
Litz wire, and he had the ohms on that inductor was like 800 or something.
When you look at the machine, it totally defies logic because the rotor is 7,000 pounds. He's using these tiny little 9-volt dead batteries.
It does defy logic.
And
it does.
It's moving such a huge mass. So obviously,
but only because our logic doesn't understand how high voltage can push through a high resistance coil.
Well,
which is what he was using.
The energy lies within the mass. That's what he was trying to get across to everybody.
Well, he had a
Yeah.
very wide coil, creating a very wide magnetic field around a
Right.
very wide array of magnets.
Right, which creates a huge electromotive.
Huge torque.
Yeah.
Right, with very little energy.
And then it can
As long as you
build
can get 1 joule through from one end of the wire to the other, then you're going to have the magnetic field
And
appear.
he had a good demonstration. What he did
In
was
the
he
way.
showed the big machine. He says, okay, I'm going to get this small motor here, 12-volt motor, and he hooked it up to a 12-volt battery, and he ran the big machine and he ran the small motor at the same time. Guess what motor died first? The small one. It also burned up.
Yeah, because it has low resistance on the coil. Eats up all the energy.
Eats up the energy, and it also created a huge amount of heat and destroyed the entire setup. So that was
What you need in locomotion is torque. You don't need RPMs. Our whole, as humans, when we build locomotive devices, our heads are thinking one thing: RPMs. How fast did that wheel turn? We're not thinking torque. You know, and that's where it's at. It's in the torque, because that can be converted to RPMs through gearing, like you couldn't believe.
Yeah,
It's
the only
peanuts.
way you do that is energy to mass. You put a high voltage into
Newman built a torque generator, a 100% torque machine.
Yeah. They would have been, if you were able to carry on with this research and get more funding. Yeah, the motors are going to be expensive, but they're extremely efficient. Everybody thinks the smaller motor is more efficient. Actually, it's the opposite. That's what Newman says. Everybody thinks the small motor is the more efficient motor. No, it isn't. It's the larger motor.
Right.
So,
I mean, now they can make magnet wire the size of thinner than a human hair.
his motor, he said, for the best effects, you must have minimum 270 pounds of copper in your
270 pounds.
Yeah, to get the over unity effects. Yeah.
Must have took them a few years just to build that coil. Huh?
Well,
Find
the
all
one,
that.
well, don't forget he did the big one. That was 7,000 pounds of copper wire.
Where did he get that? All that wire.
I have no idea.
I mean and it was all Litz wire.
No, it's regular copper.
What you don't know the gauge. It was a thin gauge though, right?
Yeah, it was a pretty thin gauge. He didn't
30
use
or something, 28.
something like that. I think he even used some thick wire too, because he says thick wire will carry the current faster. So, I guess a thicker gauge.
It doesn't matter what you use, thick or thin, as long as you put them all in series and get your ohms up there.
Yeah. So
get your resistance up higher.
The wire can't be welded into pieces, right? It has to be one straight line.
I imagine he had to do it in sections. It wouldn't surprise me if he had to, because
7,000 pounds of wire. There's no way.
That's a lot of wire, man. That's a lot of wire.
He
Like
probably welded the two ends of many wires together to make one wire.
Like that wire that they use for like internet underneath the oceans, like that big cable,
Oh,
like the
that's a little big. That's all fiber optic, actually.
Yeah, don't they have the wires in it too?
No, it's all fiber optic now.
Well, I mean, the old phone wires were copper, but now they're fiber optic.
Yeah.
Mm.
The phone wires are like 28.
But
28
originally, when they were trying to lay down the copper wires to connect North America with Europe, they had many failures because the wire just kept breaking. It wouldn't carry the voltage. They had a huge.
The thinnest wire, Lulu, the thinnest wire you can find, if you can find it, is Litz wire, Litz. That is the thinnest wire that is ever made, I believe.
Yeah, it's fibrous.
Yeah. And
it's what great. It's great. For
anybody that replicates the Newman motor, they get the Litz wire to do it. It's super thin. It's got a like a paper insulator over it, and comes in a roll already. So you don't. I don't think you have to wind it either. If you can get to the two ends, you know. But yeah, I mean, if I were to do a Newman thing, I would use Litz wire.
Yeah, but that would be a lot of work. Like,
Well, I mean, if you could find a roll that it's already rolled up and the two ends are accessible, that's
Like,
perfect.
even at the scale that I'm working at, like my coil's only 1 pound, but I'm using higher voltages. Everybody's hung up on 12 volts. Got to go to at least 24 volts and above. Ideal voltage is about 36 volts for the small motors. As soon as you get into several pound coils, then you got to go even higher, 50, 60, 100 volts. Then you'll see the effects.
As soon as your resistance builds up, you know you need to raise your voltage to get your current through there. That's because of the resistance increases.
Wouldn't it be easy to wind it with like a hand drill, like just to attach it to, let's say?
Yeah,
Yeah.
I have a coil winding machine I made. I actually rebuilt one just recently. Actually, let me grab it and I can show you guys what
You could do it with a hand drill too. It's not the easiest way, but it's easier than doing it manually.
Bear with me for 1 second. I'll bring it out and show you.
The thing is with a hand drill, the spool has a hole in the middle, so you just got to find a bit that fits the hole. Or what I do is I put a cloth on the bit so it snugs into the hole of the spool, and it spins loosely. So you know, if the wind starts getting messed up, you know it doesn't keep spinning on you. It'll slide. Give you a opportunity to stop the drill. But ultimately, I want to make like a winding machine
Okay, I got my
with
coil
little
winder right
motors
here.
and stuff.
You can see the motor there.
You made a winding machine.
Counter. Yep. It's got a foot pedal so you can start and stop it. You got speed control. I got the timer on it. Or
How long
counter.
did that take, Mike?
Not
That's
long.
cool.
Yeah, about an hour.
An hour? You're joking. Took a
Okay.
week, didn't it?
No,
An hour a day
an hour
for
if
a
you got
week.
it. 1 hour. Didn't take.
Oh, you.
Well,
But you had you knew what you found this a kit somewhere or what?
No,
you
this is all
3D
homemade.
printed.
That's 3D printed.
So you thought it up before you went at it.
Yep.
You what printed the parts or 3D or?
Yeah, I'll show you. Hold on. Let me change my camera here.
They have coil winding machines you can buy also. It tells
Yeah,
you
they're
the turn
super
counts.
expensive.
No, like $80. It's not electricity. It doesn't run with electricity. It's a manual.
So I
manual.
got my speed control there. There's my foot pedal, so I can put that on the ground so I can start and stop it. I got the threaded rod. I put the coil here. I fasten it down. I 3D printed this. It's got 2 bearings to hold the shaft. There's my counter.
You bought that counter somewhere?
Yeah, I just bought it on Amazon. And got the big motor there. Runs really good. That's it. Very simple and it works well.
Very nice.
Yeah. Not bad for an hour's work.
How much was the counter?
The counter, $20, $22, I think.
And the motor?
Motor, that's $30.
Yeah, you see, you spent less money to build that than a manual one that I had to buy. Does the same thing, and you got a better deal out of it.
Yeah, and
But-
I could also go in reverse too. I can switch the direction on it.
Having a motor is way better than having to spin it with your hand.
Oh, yeah.
You can-
And what's
Mhm.
great is I can control the speed with the speed controller, so I can just get it to a nice RPM, so I
Right.
can wind
That
it
way you can make a
properly.
nice smooth
And if I screw up, then
overlaps on your coil.
I could tap on the foot pedal. It will shut it right off. so you can regauge yourself.
That's important. Yeah.
So in theory, you could attach the a charge disc like you were suggesting before, make it spin and see if there's a weight change.
What's that?
Remember
What-
when you suggested to for me to make a charge disc spin?
I'm still trying to figure out what with the motor itself, or
The MHD.
You remember the MHD when you suggested to make a charge disc spin?
oh right, yeah. So this is an aluminum disc, right? So you would put like a brush on it, all right, and then that brush should be attached to a Van de Graaff generator. So as
Yeah.
you're spinning it, you're hitting it with high voltage.
Oh, okay.
Now, if you make this disc into almost like a capacitor, like Townsend Brown did, where he did multiple layers of aluminum, paraffin wax, tar, a whole bunch of materials, and he actually made that spinning wheel into a capacitor as well. So now it's going to hold electrostatic charge. So he would hit it with 100,000 volts and then let her go.
Yeah. Nice. I'll check to see if it's already done.
So if you step back when you hear the word 100,000 volts, you're like, whoa. There's no amps there, you know.
Yeah, it's
Yeah.
like
You'll feel the
that.
zap and you'll jump back, but you're not going to get harmed by anything. It's just
And I'm actually thinking about building myself a Van de Graaff generator. They're not hard to make.
it's 100,000 volts with no current, so it's not going to damage your equipment. It
Like,
won't
put it-
damage the MHD, but it will damage
Yeah,
any
it's like-
circuitry. Any circuitry it will damage.
It's like getting out of your car and you get zapped by your car door when you get out, you know, that electrostatic shock. I've had a couple of shocks that really hurt. You know, probably put out a lot more current than a Van de Graaff generator would.
But you can't be too close, otherwise you're gonna get a discharge.
Yeah, your hair will start sticking up. But yeah, like, you know, you can make stuff simple like this to make your life a lot easier. I you know, came up with this design in my head and slapped it together. At the motor, threaded rod, at the speed control there. Went out, bought myself a foot controller. Then I bought the timer counter on Amazon. 3D printed the hub at the other end to hold the shaft in place. That's it. It's done. Simple.
Nice.
Less than
That's
$100
awesome.
bucks.
I got
100
this
bucks?
here.
$100 for that?
Less.
Yeah. How
It's
much
going
did
to be
you
my
pay?
next coil here.
How
What
much
was that,
did
Philip?
you pay, Mike?
It was about $30 for the motor. About $22 for the counter. And it was about $20 for the speed control, and the foot pedal was like $5. So yeah,
Mike from Florida, how much did you pay for yours?
The coil winder, the manual one, is $80.
Okay.
It's like an old school one made out of
Uh-huh.
iron and gears.
Okay.
Got it on eBay, I think. This is going to be my next coil, 28 gauge, 5,000 feet. Um, 2.5 pounds. I'm hoping it's over 100 ohms resistance.
Is that copper?
Yeah, it's copper magnet wire.
Okay.
And it's 28 gauge, very thin.
Do you have a
It
multimeter?
looks kind of red from here. The color.
Yeah,
Yeah.
they red or green. It depends on the enamel coating.
Do you have a
That wire-
multimeter
that
to
wire is
measure the?
expensive.
Well, I can't get to the other end of the wire. It's in, you know, I gotta wind it onto another spool first. Then I
Yeah, I
can.
hate when they do that. I wish they would
Yeah, right.
have a extra. Oh, that drives me nuts. And the wires.
And I
get
have a spool. I have a
expensive.
spool coming for it. It's It's about that much big around the spool with a core about that big.
Yeah.
It's so it's going to be a
The wire is
wide
expensive.
turn on this coil. And hopefully I get a nice high voltage spike from it.
I'm just gonna scoot up for a quick smoke. I'll be right back, guys.
And it's very thin, so it's
But
not going to consume a lot of power, you know. That's the whole point. If you don't want to use power. You just want to use minimal power to get through the wire on a pulse to create that flyback effect, that high
okay.
voltage spike. And then you send that high potential rested over a battery or something like that to do your experiment. But this is 5,000 feet, so it's like having a 5,000 foot antenna, you know, wound up into a small space.
I do have an antenna in
Because that's essentially what coils are. They're antennas, you know.
Yeah. Originally, I wanted to generate how do you call that? Like low wave frequency.
ULF, ultra low frequency.
Yeah, ultra low frequency. But you need like a huge antenna for that.
Right. The coil or the antenna has to be very, very big. Right. Right. Exactly.
Yeah.
So this is 5,000 feet, so it can do very low frequencies because it's a very. See, the lower the frequency, the bigger the wave form of the frequency.
Yeah, exactly.
It's physically bigger. You can't see it, but it's
Yeah.
it's much bigger wave, you know. But a higher frequency is a very small wave, so whatever the height of the wave is the height your conductor needs to be to receive it. So the antenna, if it's a gigahertz wave, it's a very narrow wave, you know, very small wave. So like a small piece of metal can pick up the gigahertz, but if you want to pick up a low frequency with a very big wave on it, well, you're not going to pick it up if you don't have a very big antenna. And yeah, so yeah, a very many feet on your wire gets you lower and lower frequencies.
That's
as
true.
well as the high frequencies too. You clip out the low frequencies to isolate the high frequencies through the same long piece of wire. You know, it can pick up the low frequencies and the high frequencies, whereas a short piece of wire can only pick up the high frequencies, and you don't have to filter out any low frequencies because it's not picking them up. It doesn't have the geometry to pick up low frequencies.
Okay.
In other words, a piece of wire that's 1 foot long is going to pick up a waveform that's 1 foot tall or has a 1 foot size to it.
Yeah.
And that's like a kilohertz wave or something. Radio waves.
Okay.
It's about that size. You get into the gigahertz and the megahertz. Like megahertz waves are like, the size of a human hair. They're very small waves.
Yeah. But yeah, so that's that was my goal to using an electro-optic modulator to convert high frequency wave into lower frequency wave, but of higher energy density. They just overlap and a little bit more, and that's how you can teleport energy. You can convert them back and forth into lower frequency waves of higher energy density, and then convert them back into high frequency waves with low energy density. It's very simple, and the technology exists. We just need to connect the dots. Can you imagine having a teleport energy, like from your home to your car or your plane, and you
If I
never.
were to do that, if I were to do wireless transmission of energy, I would think the low frequency would be the easiest way to do that because
Yeah,
it can
because it
go
goes
farther. It can go very
through walls.
far. Yeah.
It goes through
Yeah.
walls, so it's
Right.
not being stopped by by walls or anything material.
Well, high frequency can go through walls also.
Depends on the frequency,
Yeah, it depends
mm,
on the frequency, but yeah,
but
they can go through walls too.
the lower frequency waves are more likely to go through walls.
Well, lower frequency wave, if it's the size of 3 houses and it goes by your house and it's the size of 3 of your houses, only 1/3 of that wave is going to go through your house.
Why
The
don't
other
they use
2/3.
this method to like charge the space probes? Like for example, like the Voyagers. You know, they always say, "Oh, they're running low on power." Well, if there's such a thing that you could, you know, transmit energy from one place to another, like why can't they use that method to charge those things?
I think they
Because
are. I
they're
mean, you use a carrier wave to send your signal wave, which then charges the other location through the signal wave.
So then, like, why do they teach like the wrong understanding of how, you know, because they say it has like a plutonium core in it, or uranium or something like that. You know, is running
Because they
out of
like,
energy.
space programs, they go for redundancy. They're not going to rely on a wireless transmission of energy. They're going to rely on more than just that. They're going to want the energy on board also.
Yeah,
They
I know,
have
but if like the idea, then it cannot run out of power if we have a different method of sending energy to it, right?
right. And I'm sure they have the backup to send wireless energy. You can do that from the ground to up there. Yeah, you beam it up there. But they're not going to rely on that because if there's an emergency, that kind of system is not automatically up and running. It takes tuning and all that stuff.
Mm.
It's very risky to go up there in space, I would think. So they want to have that energy on board, even if it's nuclear. It doesn't matter. You run out of energy in your craft, and you're not going to make it back to Earth.
No, I know.
You know.
I know you have to have something, you know, on the craft, but I'm saying like an external way to, let's say, if the energy on the craft is not working properly, or you know, whatever, you know, like to have another
Yeah,
form.
backup.
Yeah, like yeah, this is cool. I like this. Thank you.
Wireless is the best way if you can do it. I mean, but why go wireless? Why rely on a wireless transmission for your power when you can just build some kind of receiver that can pick up signals that come from anywhere? They don't have to come from a transmitter. I mean, there's signals everywhere anyway. There's stars ejecting all kinds of signals, and
yeah,
it's
but
just
I mean,
it's
there's not
full of
just
signals.
cars. There are planes and jet fighters and all that. You could remotely supply energy to a jet fighter, and then never has
Oh,
to go down and refuel.
better than remote power, ubiquitous power. In other words, power that's not remote, it's ubiquitous. So there's signals everywhere. Everywhere in space, there's a signal going on from somewhere. If you can create an antenna or electronics to absorb that signal through the antenna and turn it to power, you don't need to rely on a transmission base somewhere sending you power. You're just using the signals that are readily available through the stars everywhere, the signal waves that the stars are creating. Why is nobody, trying to use coils to receive these waves and then, rectify them and all that and work on that kind of stuff? That's redundancy, because you're not relying on a transmitter somewhere. You're relying on the cosmos, which is full of signals, to get your energy. And all you need is a signal wave to make energy. That's
Yeah.
just what I'm trying to drill home
I
there.
think that's brilliant. I think this is nobody talks about it. I've never heard
You,
about the
you know, the solar
possibility
energy is
of
going
it.
to create all kinds of distorted signal waves. Of course, it's hard to clean all that up, and
Well,
it
so
could
you make a
damage your equipment, but it's not
well, say you
impossible.
make a power cell like this that never runs out of power, then you don't have to worry about your energy. I think it'll boil down to a solid state
Well, you need
device.
water for that, though.
Well, eventually we'll come up with a system that doesn't need water. It could be
Doesn't need
completely
water.
solid state, right? And yeah, it's solid state electrolyte and make it like a Zamboni battery that can last 200 years, right? So,
It's better to
You
have
know,
more than one power source.
I'm asking this because they shut down some of these instruments on these probes to can conserve energy. Well, if there's a way that that they don't have to shut these instruments, to attain energy, then why not use that?
Those
And
probes
have
don't have solar panels, huh?
I think it does, but it stops working after a certain.
Yeah, right. They go bad or whatever
Yeah.
after a while, and then they got no way to recharge. You're saying
Mm.
that's well, that's why they're doing this nuclear thing, the nuclear battery. If they can get a nuclear battery on these probes, they don't need to rely on the solar panel, and they're very durable, so they're more likely to be able to,
well, they
keep
did.
their
They used
things charged.
they used the nuclear batteries on those rovers that are on Mars, and they seem to be performing pretty good.
Oh, they're
After,
using solar panels before. Now they got these nuclear batteries, huh?
yeah,
Yeah, because those are on they're on land. I'm talking about the ones that are just traveling through space, not
yeah.
not
Yeah,
on
those
on
probes
the
were launched before the nuclear battery technology was
Yeah.
yeah.
available.
I think back in the 70s.
It's
Yeah,
only
they're
going to get
using
better
solar
and better.
panels on those things.
Yeah,
That's crazy.
it's only going to get better and better as time
Wait,
goes, right?
wait, so they're still running even though the solar panels were damaged and they
Yeah.
still have power
Well, they're still getting some. I think the biggest problem is getting sand or dust residue covering the
off the
solar.
panel, right, right.
Yeah,
So they're
they're
still getting a little bit of power from the same
yeah,
panel. It's still working, but it's got all kinds of dust on it.
right. So they got to come up with a solar panel that doesn't get dirty. So if they
So
can do
space
that,
dust.
yeah, like on the moon or say on Mars, there's dust that's flying around all the time. So that's what happened with one of the rovers. The solar panels got so dirty it couldn't recharge itself.
I think it's just get rid of the solar panel. They can use, the same kind of device as your battery there to do
Yeah,
this. It's better than a solar panel.
yeah.
Only thing is
Char-
the water. The only issue you have is the water. But if you're in
Well,
space,
right now, eventually, I'm going to get rid of that aspect of the battery completely. It's all going to be a dry cell, right?
yeah. Well, what do you plan on using to make that work? For
Well,
without water?
I've already started on that type of electrolyte. It's PEG, manganese dioxide, a little bit of salt, and I've got some.
And a little bit of water to mix it up, right?
Well, that's only if you're using magnesium. See,
That water they use to mix it up is going to evaporate.
right, it's going to dry
Eventually.
up. It becomes it'll harden. Become like a crust. It'll dry up. That's the whole.
But isn't there already water in space? Don't these probes develop ice on their?
Yep, they could. They could.
So they could just create the same type of battery and let the ice form around the battery, and it would never dehydrate, and it would always put out power in space.
Yep.
Ice is water, hydrogen, yes, hydrogen and oxygen. There's no oxygen
Yeah.
in space, though. How does ice form in space? Maybe that's just Hollywood, you know?
Yeah.
There is no ice in space because there's no oxygen. How do you get water in space without oxygen?
Exactly. Ice could only be on a celestial body, right? Anyways,
Not in
guys.
space. There's no oxygen in space.
Yeah.
And
Well,
you need oxygen to make water, and you need water to make ice.
yeah. Depends on
Unless there's a hydrogen ice. There is dry ice, I guess.
Yeah.
So will these
Anyways,
cells work off of just hydrogen, or do they require the oxygen too?
what the batteries on those rovers?
The
No,
battery
sure.
cells.
What these ones? It's
Yeah.
just the solid state electrolyte. I have magnesium in these guys. So I'm trying
What do you
to
think though when you put the water in there? You think that they're using the hydrogen out of that water to make the power, or they're using both the hydrogen and the oxygen?
well,
I
from
think
what
it's
from what
maybe
I
a hydrogen
understand,
alone.
it's both. It's both. You have to have the air.
Because a standard fuel cell only requires hydrogen, and
Yeah.
liquid hydrogen. No oxygen.
This is just a different type of battery, right? Like I'm experimenting with different combinations, what I could use, and what the power outputs of different combinations. I did a lot of experimentation this week with it, so I'm going to stick with these batteries for a month and see how they perform after a month after they completely dry out, and see what kind of values I get out of it, and we'll go from there. I printed up the new cases to make different combinations of stuff. Try those out and see how they work. I've got barium titanate powder coming in, a piece of electric powder, and I'm going to add that to the solid
Sodium
state mix
hydroxide.
and see what happens. So if I can get that quantum tunneling effect, then I can make a completely solid state battery that would never run out of power.
You should
So
see if sodium hydroxide powder activates the cell.
yeah, that's a different element that you can test.
I mean, it's hydrogen and sodium. What I'm saying is, I'm trying to figure out if oxygen is required to run these cells.
See, in this mix here, have manganese dioxide. That's what they used in the Zamboni batteries back in 1700s.
So that's oxygen dioxide.
And his battery is still working today, 173 years. It's still putting out power. So they got it at the Oxford Museum. The original cell that he made is still running today, 173 years later.
And he didn't use any liquid, huh?
Nope, totally dry cell.
Magnesium
No
dioxide.
magnesium. No, he used manganese dioxide. He used silver plate, and what was the other one? Silver and zinc. Those were the two plates, and with a piece of very thin cardboard soaked in manganese dioxide, and just stacked like 4,000 plates. He made two cells, and they're still putting out power today. Almost 2 centuries. Century and 3/4.
Silver doesn't corrode, neither does zinc.
Is that like the Casimir effect when they put the plates next to each other or
No,
whatever?
quantum tunneling.
Quantum tunnel.
It's almost like an electret, if you know what an electret is. Basically, it's a composite material that holds electrostatic charge. So those Zamboni batteries, when they're brand new, they could put up to 2,000 volts of electrostatic field. Actually, one guy on YouTube made one, and he was able to put a neon bulb beside it and actually lit up the neon bulb because it created such a big electrostatic field. So they're an electrostatic battery, and the guy says he could charge up capacitors really, really good with it. So that's a different. I'm finding a lot of these old inventions, like talking back 100 years ago, they were onto the right stuff, and it's just over time this knowledge gets lost. And I think it's time to bring some of that stuff back because it seems to be working. So these are kind of in the same kind of ideas as a Bomi battery, but I'm just using different elements right now, testing. So it'll take a lot more testing to get the right combination to make a battery that won't die. Like even if the battery would last, say, a century, hey, that's pretty good. And they could actually do work, right? Anyways, we're about an hour, 2.5 hours into the show. I think I'm gonna call it quits for the night. I'm getting pretty tired. Philip looks like he's half asleep. So I think we'll call it quits for the night. Everybody, thanks a lot for joining us, our panel. Philip, thanks a lot for your presentation. Mike, and we got Lulu on again. That was great. Thanks.
Yeah, thanks everybody.
Yeah, thanks.
Thank you.
Thanks
Thanks,
for
everyone.
all your knowledge, and yeah, we'll do it again next week. Hopefully, we'll get Gerald on. I was hoping he was going to be on tonight, but he didn't show up. But well, we'll see what happens. Maybe next week. Yeah, we'll do this show again next Friday night at 9 o'clock Eastern. Just tune to Faraday Research for all the updates and projects I'm working on. Don't forget to check out Mike Does, his YouTube channel. And hopefully we'll see Philip again next week. Maybe I'll do some other experiments he can share with us. Everybody, thanks a lot. Have a great night.
Have a good night, guys.
Take care.
Good night.
Good night.